There are two ways of looking at ages when evaluating geologic materials. In this video, we will look at determining relative ages, which means we will be looking at determining older versus younger age relationships when looking at a series of rock in something like a cliff or the side of a valley. To accomplish this, we will use what are known as Steno's principles, written by Nicholas Steno back in the 1660s. The first principle, which is so intuitive and almost goes without thinking, is looking at the older versus younger age relationship where oldest rocks are on the bottom and younger rocks are sitting on top. So the limestone with the bricks here would be the oldest, the sandstone would be the second oldest, and then the shale up top would be the youngest. Now in reality there are processes happening on the earth that can overturn these rocks and actually put younger rocks underneath older rocks. But for the purpose of an intro geology geologic time lab, for us we will always have oldest on the bottom, youngest on top. But I want you to be aware that in geology, if you go outside, you're looking in mountains, this might not always be the case, but it is most of the time. And for us, again, at the intro geology level, it will be the case when we're evaluating our cross-sections. The next principle is the principle of original horizontality. So what this is saying is that these rocks stacked up and were built in nice flat horizontal layers. If we see something in a cliff or a mountain that has rocks that are not sitting horizontally, the rocks are at an angle, we know that some kind of major event has taken place, that the rocks started out originally being horizontal, and then they were either tilted like these rocks are, they're not sitting horizontal. Folding, we would have curved contacts because we'd actually be folding or squeezing the rock. So we look at the series of events. This rock was placed first, this rock came second, this rock came third, and then the tilting or folding is actually an event by itself, which would be younger than the rocks themselves being deposited. Now, tilting and folding, a major geologic event, often is due to plate tectonic activity. We have a convergence that causes uplift at the edge of the plate boundary, which then causes the rocks to tilt towards that convergent plate boundary. In our next principle, we have what is called lateral continuity. So here we have three layers of rock. We have a valley, and let's say we're standing in the valley, and we evaluate the rocks on each side of the valley, and we find that they have all of the same characteristics. They have the same minerals, they have the same sorting, the same roundness for maybe the sandstone, they have the same set of fossils within them if we're looking within the limestone. So the principle, although it kind of seems intuitive to us today, but it wasn't always that way, is that the rocks on each side of the valley are the same layer, and they have been eroded or cut away in the middle. So when we're standing in a single valley like the Grand Canyon, this is kind of easy to see because you can see each side of the valley from where you're standing. You can see the colors of the rocks and how they coordinate and correspond to each other in different parts of the valley. Excuse me. But when you look at something like what Alfred Wegener did with continental drift, he looked at matching geology on opposite sides of ocean basins. He looked at mountain belts in eastern North America like the Appalachian and matched them to the rocks that make up the Scottish Highlands all the way across the Atlantic Ocean. So for him, his valley was the Atlantic Ocean, and on each side of it, even though the distance was so great, the rocks still matched. So applying the principle of lateral continuity to a much larger scale. So in the order of events, we know that the rocks must have been deposited, starting with the oldest at the bottom. So we would give this one maybe a number of 1 for the oldest, then 2, then 3. And the erosion that came in here is younger than each of the rocks that has been deposited, because they had to be there to be eroded. Which leads us into our next principle, which is the principle of cross-cutting relations. And an important note to make for this one is that which cuts which for us in this image is a fault, that which cuts is younger than that which it cuts through. So for this image, the fault is doing the cutting, so it must be younger than the rocks which it is cutting through. So this time we have numbers on the figure, 1 being the oldest, which is the rock on the bottom, 2 being the next oldest, then 3, then 4 is the youngest. So each of these rocks had to be deposited, and then the fault comes in to cut and displace them. So think of it kind of with an analogy of scissors and paper. If the paper does not exist yet, the scissors cannot cut it. Just as if the rocks do not exist yet, the fault would not be able to cut them. So the rocks have to be older, the fault has to be younger. And our last principle that we're going to cover for Steno's principles is the principle of inclusions. So here we have two very similar cross sections. You can see that there's a shale on the bottom that's colored blue, and then we have an igneous intrusion or an igneous rock that has been made that is then topped by a sandstone. So first let's focus on these little red dash lines. The little red dashes represent contact metamorphism, meaning the igneous rock baked the rock where we see those red dashes. Now, the baking itself is not an event, it just tells us about the order of events. So let's focus on this one first, right here. You can see that we have numbers again corresponding to the order of events from oldest to youngest. So 1 is the oldest, the shale. Then we have the sandstone as the next oldest, with the igneous rock as the youngest. Now this does not follow the principle of superposition, because superposition says oldest on the bottom and it gets younger as you go up, and here we're not seeing that remain constant. The principle of inclusions, along with the contact metamorphism, is what we are using to determine the ages or the relative ages of these layers. And the principle of inclusions, you should make note, states that which is included, the pebbles, are older than that which includes it, which in this case is the igneous rock. So the shale and the sandstone have to be in existence, they have to be older than the igneous rock in order to be included in it. So when we look at this example, we are going to call it a geologic term, which is a sill. A sill is an igneous intrusion that runs parallel to the rock layers that are present. So essentially in the past, the shale and the sandstone were against each other. And what happened is the magma came into the region, and the sill, or the magma, forced its way between these two layers, which is what caused them to break up and have fragments, or what we call xenoliths, in the sill. And so the sill, the material, is younger. And think this material is intrusive. So when we're looking at sills, we're looking at rocks that have phaneritic textures. So it may be a good idea for you to review igneous rocks and look at the rocks that have phaneritic texture, because that will help you determine the relative ages of the rocks and their order. On this side, you see that there's a bit of a difference from over here. We only have contact metamorphism at the bottom. Instead of having nice smooth contacts, we have a very rough jagged contact, and then our numbering is different. 1 is the shale, 2 is what we call the unconformity or the erosional surface on top of the shale, 3 is the igneous rock, 4 is the unconformity or erosional surface on top of the igneous rock, and 5 is the sandstone. You also see that we do not have any inclusions of sandstone in the igneous rock. So what that is telling us is the shale is the oldest of the rocks that we have in there. The igneous rock came in next, and then the sandstone came in later, meaning it's younger than the igneous rock. This time, instead of looking at a sill, we are looking at what we term a flow. A flow is different than a sill. A sill happens at depth, as an injection between rocks that are already there, whereas flows, as the name would tell you, come from lava flows at the surface of the earth. So sills are at depth, flows are at the surface. So what happened was the shale was the surface of the earth at this time. It was getting broken up, weathered, eroded, and so there were little pebbles being made. The lava then came from the volcano and flowed over the shale and picked up some of those pebbles and included them within its body. The lava flow then became the surface of the earth and went through weathering, and then the sandstone began to be deposited when conditions changed from an erosional environment to a depositional environment. So when we look at flows, we're looking at extrusive igneous rocks that would have an aphanitic texture. So again, it would be a very good idea for you to review what igneous rocks have aphanitic texture, or one of the other extrusive textures like vesicular, glassy, pyroclastic, so that when you look at a cross-section, the texture of the igneous rock in conjunction with the inclusions, the contact metamorphism, and the presence of unconformities will help you determine the correct order to put those rocks in for relative ages. These are the 5 Steno's principles that we will use and apply to geologic cross-sections that may have 15, 20, 25, 30 events that you have to put in order from oldest to youngest that you can expect to do in an intro geology lab.